Hello everyone. It is 20,251,260 Tuesday. I am your host Nino, and today I am introducing a training article from the archives. It is getting colder lately, so I hope you are all staying warm with some hot coffee. Actually, I spilled mine earlier, which is why I'm standing while recording this. Anyway, let us dive into the world of technology. Today, I have a super interesting paper to share with you all. It is about making artificial intelligence faster, like way faster. We all use AI these days, right? But have you ever wondered how fast it can actually go? Is there a speed limit for AI? Now this paper answers that exact question. The title is Speculative Decoding Speed-of-Light, Optimal Lower Bounds via Branching Random Walks. The call is Receive advanced 12.11,718. Okay, let us break this down. It sounds a bit complicated with words like branching random walks, but trust me, it is fascinating. So you know how large language models LLMs work. Usually they generate text one word at a time. It is like, the AI thinks of the first word, then looks at it and thinks of the second word, and so on. This is called autoregressive decoding, but this is slow. It is like typing with one finger. You have to wait for the previous word to appear before you can type the next one. So smart engineers came up with a trick called speculative decoding. This is the main topic of the paper. Imagine you have a big, smart, but slow boss, a quick, energetic, and maybe a slightly less smart assistant. The assistant guesses what the boss is going to say. The assistant drafts a whole sentence instantly. Then the boss just looks at it and says, yes, no, yes. The boss verifies the draft in parallel. Because checking a draft is faster than writing from scratch. This speeds up the whole process. This technique is already used in things like vLLM and Eagle. But here is the problem this paper is trying to solve. We did not know the limit. We did not know how fast this could possibly get. Is there a ceiling? Can we just add more computer chips and make it instant? The authors of this paper, Sergey, Pankratov, and Alistarh, did some heavy math to find the speed of light for this technology. They used something called branching random walks. Basically, they modeled the AI generation process as a tree of possibilities branching out. Here is the really cool insight they found. The speed limit depends on something called entropy. Entropy is a fancy word for uncertainty or randomness. If the AI is very sure of what it wants to say, like reciting a famous poem, the entropy is low. In this case, the assistant can guess correctly often, and the speed up is huge. And if the AI is being creative, or writing something unpredictable, the entropy is high. The assistant makes wrong guesses, and the boss has to reject them, so the speed up is limited. It proved that even if you have infinite parallel power, even if you have a million computer chips working together, you cannot break this speed limit imposed by the uncertainty. The speed up only grows logarithmically with the number of chips. That means adding more and more power gives you less and less benefit. It's like trying to run through water. Eventually we'll hit a wall. Now, let us talk about how this applies to everyday life. You might be thinking, I know, why do I care about math bounds? Well, this dictates how responsive our future gadgets will be. Here are 3 specific examples of where this technology is crucial. First, let us look at machine translation. Imagine you are wearing smart glasses, and you are talking to someone who speaks a different language. You want the translation to appear instant on your lens. If the system is slow, there is an awkward delay, and you stare at each other weirdly. With optimized speculative decoding, the AI can guess the structure of the sentence ahead of time. This paper tells engineers exactly how much hardware they need to make that translation feel instantaneous, without wasting money on chips that won't help. Second, think about chatbots and dialogue systems. These are programs that communicate with humans in natural language. We all talk to voice assistants, right? Sometimes they take a few seconds to think. That silence is painful. I always wonder if they ignored me. For a conversation to feel natural, the response needs to happen in milliseconds. This paper helps developers understand the limits. If the chatbot is answering a simple factual question, it can be super fast because entropy is low. If you ask it to write a creative story, it will naturally be slower. And now we know why. It is not just a slow computer. It is a fundamental law of probability. Third, there is information extraction and text summarization. This is technology for extracting necessary information. Large amounts of documents are creating summaries. Imagine you have a 100-page PDF, and you need the key points right now for a meeting. You upload it to an AI. Using speculative decoding, the AI can race through the document generation. It predicts standard phrases and formatting, skipping the heavy lifting for the predictable parts. This paper confirms that for highly structured tasks like this, we can achieve massive speedups, saving you time and stress before your boss asks for that report. The paper also compares this to other technologies. Before this, people just looked at the average acceptance rate. They said that the assistant is right 60% of the time, so it should be this fast. But that was too simple. It did not account for the branching paths of probability. This new theory using branching random walks is much more precise. They actually test out real models, like Llama 3 and DeepSeek. They found that their theoretical limit matches very closely with the best current systems, like a system called Eagle 3. This means our current tech is actually getting close to perfection. We are nearing the speed of light for deterministic algorithms. That is pretty wild, isn't it? It was like we had been building faster and faster cars, and now someone calculated the maximum speed allowed by physics. The authors show that simply throwing more cars at the problem is not the answer anymore. You need better models with lower entropy. I need smarter eyes that are less confused if you want to go faster. Alright, I should mention the math a bit more simply. They found a formula. The expected number of tokens per step is roughly the logarithm of your parallel capacity divided by the entropy. So if you want to go faster, you either increase the capacity exponentially, which is expensive, or you decrease the entropy. I find it really cool that they use random walks to prove this. You know, a random walk is like when you're lost in a city, and you flip a coin to decide which way to turn. Eventually you end up somewhere. I once tried to go home by flipping a coin at every intersection. I ended up at a Baytown 3 times over. That was a delicious mistake, and not very efficient for getting home. That is my little joke for today. I hope someone got it. Anyway, to summarize, this paper is a big deal for the future of AI efficiency. It tells us that we cannot just brute force speed forever. You have to be smart about uncertainty. It validates that techniques like speculative decoding are the right path, but they have natural limits. It is a bit humbling, really. Even artificial intelligence has limits imposed by the laws of math, just like I have limits on how much coffee I can drink before I start vibrating. So next time your AI assistant answers you instantly, you can think about the little draft assistant, guessing words furiously in the background, and the boss verifying, while running a race against the entropy speed limit. That is all for today's deep dive into the archives. I hope you found this speculative decoding paper as interesting as I did. It is amazing how much thought goes into shaving off a few milliseconds of wait time. But hey, time is money, right? Or in my case, time is just more time to talk to you all. Thank you for listening. This has been Nano. Stay curious, stay warm, and try not to spill your coffee. See you next time.